Good morning, everyone. It's fantastic to be back in New Zealand. I had two great talks help set up my talk this morning from Doug and from Andrew. So I hope I can build on what they were doing. I was viciously editing my slides while they were talking to make sure it had something new in it. So yes, I'm going to talk about deep co-design in the post-exascale computing era. So what I'm going to talk about. So, 15 years ago was when we were especially looking at how we're going to get to exascale, and there were a lot of predictions made during that time. Unfortunately, a lot of those predictions were documented, and so what I'm going to do is go back and just talk about some of the things that surprised us and some of the things that we got right. And so that, I think, will be a nice springboard to start talking about the future. In post-exascale, there's a lot of changes underway in the architecture world right now. If you think about heterogeneous systems, some of us believe, this is the path that we're on. There's not really anything we can do about it. We need to learn to live with it and adapt to it. And this is enabled by heterogeneous integration and chiplets at the architecture level. This makes co-design critical. So it's really been a buzzword over the past 10 years in HPC, but if you truly believe we're going to have these very specialized systems, then the code design process itself becomes a critical aspect of that. One of the projects that I'm going to talk about is a new code design project we have underway, and it's really looking at how we can take code design from the algorithms level all the way to the materials level. And so literally on this project, we have people designing new algorithms for spiking neural networks, and we have people looking at brand new devices and neuromorphic materials that we might be able to use to implement those spiking neural networks. So let's get started. So the exascale reports and predictions. So if you were part of this process, you got a lot of frequent flyer miles. So the first report really came out in about 2007. Then there was the nice study by Peter Kogi that talked about a lot of the very specific parameters for what it was going to be, what the systems would look like, what the technology trends were. And there were a host of others that looked at the grand challenges, kind of the top 10 research challenges, as well as what a software stack would have to look like for that. And so these are nice reports. A lot of effort went into them. If we look at where we are today, you have systems back in 2012, and it's important to remember about 2010. Jaguar was the system at Oak Ridge, and it was just a multi-core system. And for someone to get an application up and running on that multi-core system, in some cases, it ran out of the box on that system. So it was MPI, OpenMP, Fortran or C. They would take their code and recompile it. And literally in 2 months, we would have 50 applications up and running on that system. That's changed, and it really started to change with the GPU era in about 2012. And of course now we're seeing more heterogeneity. We have different types of systems, different vendors with different GPUs coming online. We expect more diversity. Doug showed this slide earlier. It's an incredible number when you think about 37,000 GPUs in a system. I think the only thing that makes me more surprised on this is the rack weighs 4 tons for this system, right? That's more than most cars. And so it's a formidable challenge, both from the facilities perspective, from the hardware perspective, and from the software. And of course, this has resulted in a first exaflop system on the top 500 list. There are some other things there that you can take note of, like the energy efficiency. But it's a nice achievement. Doug also mentioned the exascale computing project, and I just wanted to highlight there, and he talked about this briefly. The application development, the software technology, and the hardware integration. Hardware integration primarily focused on accelerating specific technologies from each vendor so that they would be ready to participate in an exascale procurement. The software technology really tried to gather up a lot of the software that in some cases had been around DOE and been funded by DOE for decades, and make it more useful, package it appropriately, add features to it for GPU computing, and so on. And that's part of where my role in ECP is. I'm a lead in the software technologies. And this is, I know, a nice outcome of that is the E4S site. And I'd encourage you to go look at this site. You can see a list of a lot of the products that are available. They have been packaged so you can download them and use them in a container, or you can use the SPAC installation tool to do that. It's nice. But one of the things I'm most proud of is in my area, we're doing advanced compiler development. And so the LLVM compiler ecosystem, as we heard about earlier, is really the de facto compiler these days. And I would suggest that it's basically because of the permissive license as well as its modularity. The licensing makes it really easy for the vendors or other people to pick this up and reuse it. So if you're a small company and you want to start a new chip, you can pick up LLVM and start modifying it and redistribute it. The modularity is, I think, where heterogeneity really accelerated the acceptance of LLVM. And what I mean by that is if you look at LLVM, it really has a front end and a back end. In the middle is LLVM IR. And as long as you can generate that IR, in most cases, you can pipe it to some back end. And that can be for a multi-core, it can be for a GPU, it can be for an AI accelerator. And so we've invested a lot. This chart shows you what some of those investments are. First is the Solve project. It's really trying to make OpenMP offload work well on both the platforms that we have, Aurora and Frontier. Second is the Proteus Tune project that's looking at OpenMP, but also OpenACC, auto-tuning, SYCL, and Cocos. Next, we have Flang. And so Flang has been an investment from DOE for on the order of 7 years. And the idea is we wanted to get an open source Flang out there that was production quality and available to the world. And so that project is underway, and it's making a lot of progress. And by the end of ECP, we hope to have an F95 functioning serial compiler there. We're also working on the offloading for that. The offloading, is a little bit late, but it's doing well, so it will be available probably within the next 18 months. And then we have some other things there with HPC Toolkit and NNSA. It's interesting to point out, just to jump on the earlier comments, companies like Intel and IBM have basically abandoned their proprietary compilers in favor of LLVM. So if I would have asked you, 5 years ago, if you thought they would do something like that, you probably would have called me crazy, because GCC and the proprietary compilers were really what everybody was using. And now it's mostly LLVM everywhere. And so that's really a sea change in some ways. Another thing we're doing is continuing to work on programming models. So this is a recent result that we have. And basically we looked at taking Cocos, which Doug mentioned, and tried to map it to OpenACC, and we found some really surprising results there. I'm not showing this to really draw your attention to OpenACC, but the fact that different programming models can have tremendously different performance. And if you look at the chart on the right, it's the Lulesh benchmark with OpenMP, CUDA, and OpenACC. And in this one, OpenACC gets much better performance than OpenMP, and it's because it matches the abstractions of Cocos much better. And we see this not across just Lulesh, but we also see it across some of the apps that we're looking at now in ECP. But this is a challenge, and one I'll come back to in a moment. So predictions. Somebody yesterday was talking about the predictions, so I got on Google and was trying to figure out where this prediction quote came from, and it turns out there's at least 5 people that are credited with this quote, and so that's a couple of them. But I got several brave souls on the stage the last ECP all hands meeting in May 2022 and asked them, you know, what did we get right and what did we get wrong? And so Pete is here and he can jump in if he disagrees with some of these things. So as far as hits, so a hit is we really came in on the system power. If you go back and you think in 2007, 2010, people were talking about gigawatts. And so, you know, we're nowhere near that. The limited power for our frontier system is 29 megawatts, and it usually runs in the 20 megawatt range. And so that's a big hit. We really didn't have that many. I'm getting a little echo here. Is that okay? So the few major software rewrites. I mean, we have been rewriting codes, but the fact that we're still using MPI and the basic languages that many of these teams were using is, you know, remained. We integrated 1,000 researchers, and so that's a big task in and of itself. In one project, to have that many different types of engineers and scientists working together was a big accomplishment. And then, of course, open source software and concurrency were things that we were worried about. So misses. If you think back to that time frame, the mantra was 10 to the 18th in 2018, I believe. That's what we were shooting for. And, you know, we're a little bit late in the sense we're 4 years past that. And so, you know, if you go back and you look at some of the trends and kind of factor it in, that made our job a little bit easier. The second one was the programming systems are really multiplying, and we find a lot of them are incomplete or they're works in progress, and they're in some cases not ready when you need them. And what I mean by that is, you know, a standard programming model that's not ready when the system is made available to the users really misses the mark, because they'll go use whatever works. And if it's not the standard programming language that you want to present to them, and it takes a year to get it working, you're kind of out of luck because you missed that boat. Hardware diversity, resiliency and fault tolerance, and then, you know, we find a dwindling number of vendors capable of having $100 million plus procurement. You know, there are just not that many that can take on that kind of risk. So what did we miss? And this is maybe more important. So the productive programming models, and I'm looking at things like Python, Jupyter, Julia. You know, we all knew about Python. We invested some in Python, but the others we really didn't. The cost, if you listen to Jack Dengaro's presentation at supercomputing, he had a number that was about $4 billion. And remember, that's a lot of feature. That's non-recurring engineering costs, that's procurements, that's the cost of ECP, which Doug talked about, and so that's, you know, that's a lot of money. Almost none of the reports mentioned AI and machine learning, right? And this is where I think co-design becomes critical. If your co-design cycle is too long, you might completely miss things like that. I think if you look back and kind of look at the publication counts, about 2015, 2016 is when you really started to see that area tick up. And in some ways, you know, it would have been nice to be able to target those a little bit more agilely. And then cloud deployment models and green sustained computing, those were some of the other areas. Now, I just want to stop for a moment and ask, did I miss anything? Pete, how did it look? Anyone else have a question about the past?
If you look from Tera to Peta, it was from 97 to 2008, right? From Peta to Exa was the 14 years. And so we're kind of starting to see, you know, sort of the silicon scaling tapering a little bit. So are we going to get to Zeta in 2040? Or?
That's a good question. So, you know, and I did not coordinate with him before I did this. So I have this slide in here, right?
That's why he's getting paid.
And so the next question is, you know, here's where we are. You see 11 years to get from Terra to PETA, about 14 years from PETA to EXA. So, the real question is, if and when we'll be focusing on a Zettascale system. Now, the one thing to keep in mind is that any potential Zettascale system will need 1,000x improvement in energy efficiency. And this was the same thing we've looked at petascale. But I guess the question is, can the community come up with dramatic improvements in energy efficiency like that? And again, you think same footprint, same general power, that would be something that seems like a formidable challenge. Sure.
Microphone, please.
You were talking about looking back, and when those studies were done, blue gene P and stuff kind of dominated actually in a lot of ways. There was that low power approach.
Right.
But that's not how it turned out. Was that a surprise to you or to the group?
If you looked at the early reports, they did have 2 swim lanes in most cases. One of those was the homogeneous processor, and then the other one was some type of accelerator. And so that was on the map, and in fact, I would say the heterogeneous computing was downplayed in some sense. People did not think that was the way it was going to go, but as the procurements played out, we saw them bend in that direction. And there may still be a place for that. I think one of the big decisions early in the blue gene, early in the blue gene days was the fact that let me finish. The blue gene, early in the blue gene days was deliberately lowering the CPU frequency so you didn't use as much power on a node. And now if you look at H100 from NVIDIA, depending on what part you're looking at, you're talking 700 watts per GPU, right? That's a huge number. What were you going to say, Pete? Fugaku. Right, and you've got Fugaku as the kind of the counter example right now. But it's still about 35 megawatts, so it's a pretty significant system just in terms of facilities. But yeah, these are great coffee drinking discussion points, so good. So, thinking about where we're headed, so I put this slide together. So really the important architectural trends. So the first one is chiplets, and then heterogeneous integration is how you integrate these chiplets together. And I love the slide from DARPA on the upper right-hand side because, first of all, it's generic, but it gives you a real idea of what's happening. Today, with a lot of processors, you've got a monolithic die. And sometimes the yield on those dies is very low because they take up a lot of space and they have defects, and so the yield drops. A different strategy is to make your dies smaller and then integrate them with packaging so that you can just package up whatever parts you need. Now, when you do that, you don't necessarily have to use the same node or the same technology in that package. You can switch. So if memory needs 22 nanometers and your accelerator needs 3 nanometers, you can still put them on the same package. And that's really a benefit just from the practicality of it. And then if you look at the far right, there's no reason you can't mix custom and commercial chiplets together and integrate them together on a package. And you see some of the examples here. And this is not pie in the sky, right? If you look at most of the designs coming out recently, Ponte Vecchio, AMD, other devices, they are using a chiplet strategy there. Now the key is most of them are proprietary chiplet strategies, and so the future, we hope, will be more of a standard strategy. And what I mean by that is, if you look at some of the new standards like UCIe chiplet standard, almost all the major vendors are on that. And the goal there is to have catalogs of chiplets that you can just download and plug in and have a new processor developed that specifically fits your workload. And again, this is allowing people like AMD to announce not very long after their Xilinx acquisition, CPUs and FPGAs on the same chip this year, right? And so it's powerful. It gives you quick turnaround on a lot of these things. If you look at co-design, as I mentioned earlier, we believe in co-design. We had a workshop last year where we talked about how we could improve co-design. and there were several priority research directions that came out of that. The first one was really looking at targeting this heterogeneity, but making it really fast to be able to explore the design space and understand what works best for our workload. The second one was software and applications, and today I'm not going to talk much about software, but I have a lot to say about software and performance portability, and that's probably one of, if not the major challenge moving forward. Security, and then design with data-rich processes, and what that means is just don't create a bunch of proxy apps and drop them on a website somewhere. Tell us what the workload really is. We want real-time telemetry data about what's happening on your system today so we know what to accelerate. Because if you wait 5 years or whatever the number may be, you may miss the mark. So with that, I'll pause again and ask, are there any questions about Codesign, or for or against? Or Jim, you were at the workshop for Codesign. Did that summarize it? Oh, good. So, what I'd like to dive into now is a very quick overview of a new microelectronics code design project that I'm really excited about. It's called Abisko. Someone mentioned northern Sweden yesterday, and that's where Abisko is. It's a national park, and so that's where the name comes from. So in the microelectronics code design, what we wanted to do in this project was really try to do what we're calling deep code design, from materials to applications. And we have people involved in the project at every level of this. We have materials scientists, device engineers, computer architects, and so on. And we needed, and you see some of the partners here, but our driving problem is to develop a spiking neural network chiplet that we can integrate into a contemporary computer architecture. And along with that, we want to look at new novel materials that allow you to do that. There's a host of materials out there that have properties that appear like they can make a good neuron or synapse, and since in a heterogeneously integrated package you can drop that on there, we wanted to try that. And then we've done some software work. I'm not going to be able to talk too much about the software work today, but just walking through this, if we look at the application area, our application fortunately was a high energy physics sensor being designed for a CMS experiment at CERN, and we're working with Fermilab on this. That's part of their contribution to CERN. If you look at the raw data rates for this, it's it's extreme. If you look at this chart, you can see there's a human right here to give you an idea what the scale of the experiment is. It's a massive instrument. But if you look at the clock rate, 40 megahertz, and the amount of sensor data coming off, it's on the order of petabits per second. And of course, you need to try to reduce that somehow. One of the ideas is to try to do some machine learning or neuromorphic implementations in the digital domain. But of course, if we could do that in the analog domain, it would be potentially orders of magnitude savings in performance and power. And so that's what we're doing. We're looking at this right-hand side where we actually, before the A to D conversion, we try to use spiking neural networks to identify the features we're interested in. So our algorithms team is spiking neural network experts. They're taking the data that we see from these sensors, the particle charges from the different sensors and the arrays of those sensors, and trying to understand how you would take that and encode it in a spike train, as well as configure a neuron and synapse network so that you could, with some reasonable accuracy, identify those events. Then we have a software task, and just based on time, I don't get to spend a lot of time on this, but we're using MLIR too. So what we're doing is we're creating an embedded domain-specific language, and that embedded domain-specific language allows you to generally define what that neuron synapse frame configuration looks like, and you get an idea of this here. And because it's in C++, it essentially can be compiled on any system that has a C++ compiler and then lowered to a back end. It could be our simulator, it could be an FPGA, it could be a GPU. But part of the benefit of using MLIR is it allows us to do that. Then if you look at the architecture, it's no surprise we're really focused on chiplets. And so just to summarize that, we wanted to just, we don't want to create our own memory controller. We don't want to create our own RF interface. We want to grab those off the shelf. And then we want to have a spiking neural network device that actually may be non-CMOS, and that's what the neuromorphic materials teams are looking at, so that we can take that chiplet and drop it on there to do our spiking neural networks. Now, there's a lot of standards discussions going on these days, and like I said, we already have devices out there with proprietary interfaces, and so we think there's a lot of promise there. So just to think about what this chiplet looks like, if you look at this diagram, this is an overview of what the neuromorphic chiplet looks like, and we have a memory chiplet and a RISC-V chiplet perhaps that we'd grab from off the shelf. We have an interface logic on that particular chiplet, and then once you get into that chiplet, you have additional interfaces just to be able to talk to things like the analog interface. Now the interesting one is the actual neuromorphic element cluster, and that is what our materials and device team is looking at. If you take that particular grid there, that crossbar, our team at Sandia actually has several technologies there. One of them is resistive RAM or ReRAM, and then they also have electrochemical RAM. These are tunable resistance devices that you could put in a crossbar like this, and the benefit of that is that you can then do things like an analog cross product. And what you see here is the voltages coming in across the rows, and then currents coming out of the columns, and those currents coming out of the columns are an analog for what the multiplication is you see there in the matrix. Well, each one of those resistances that actually give you that value is one of these devices. And this device I have here is a 3-terminal device, EC RAM. It's electrochemical RAM, and actually came out of battery technology work. And so what it allows you to do is to tune that resistance to be many different values, and that's what the team is studying now. So in order to be prepared to estimate how this spiking neural network chiplet will work, we're first taking our ASIC design flow through just a digital neural network. And so what you see here is our tool chain. We have a traditional digital neural network inference system that we built. You see the different phases of it here. But if you lay it out, what you see in the figure 15 shows you what the layouts are for that. And it's both 2D and 3D. And so we're doing things like estimating power, performance, and area by using this tool chain. The next step is to really take that and apply it to these analog devices that I mentioned earlier. And so to understand the devices a little bit more, and they have a TCAD model. If you're familiar with what the TCAD model is, it really describes what the device geometry, various properties like the IR curves and things like that are that you get out of these devices. So it allows you to make larger devices out of them. And so they are looking at doing exactly this. As I mentioned, we have EC RAM, ReRAM, we develop circuits, and we even have prototypes. Those 3 devices you see there are prototypes of that crossbar that have been sent from Sandia to Oak Ridge, where we're doing probing of those devices to understand what the IR curves look like. There are things that we need to know. The first one is, if you look at resistive RAM, one of the complaints about resistive RAM over the years is they're difficult to program. So if you manufacture a specific device, you may not have a fine granularity control over the resistance of that device. And it may just be because of manufacturing tolerances or defects. And so what we're looking at is trying to understand better ways to manufacture those. There may be new boundary materials or other properties that we want to change. But what you see here is the spread of those conductances. And then finally, just looking at materials, if you look at the at Oak Ridge, for example, we have this CNMS facility that has multiple devices, electron microscopes, a bunch of different probing facilities, like I mentioned, that we were using on the devices. If you look at, for example, the EC-RAM, which is made of vanadium dioxide, you can get a very clear picture of what parts of that device are semiconducting and what parts are metallic. And the idea is that by working with the device engineers, we may be able to improve some of the properties like programmability that I mentioned earlier. There are other things that we want to understand as well, like what the retention rate is under different operating temperatures. And so there's a whole host of those things that CMOS has basically solved, but some of these products may not have good properties in. So we're trying to understand those and then improve them if we can. So with that, I'm going to conclude. So Exascale is here, break out the balloons and the mission accomplished sign. Our predictions were reasonably accurate, but as AI and ML show us, it's a fast-moving world out there, and I think these chiplet infrastructures and heterogeneous integration is going to make it a lot more competitive, and so you need to really cycle quickly. And that's where deep code design is critical, and I just told you a very brief overview about Abisko and the spiking neural network chiplet we're working on, and I think we need about 100 more projects like that one. So with that, thank you very much.
Thank you.